In this video, I'm going to give you some information about dynamical systems in the plane, particularly linear vector fields. We'll get to nonlinear vector fields later, but the linear material is a necessary starting point. So what do I mean by a linear vector field? Well, I mean that we have a differential equation for a vector that's simply a matrix times the vector. So x dot equals ax. And in most cases, since the vector arrow kind of gets distracting, we'll abbreviate this as just, say, x dot equals ax. Now, if you'll recall from elementary differential equations theory, the solution to the initial value problem x dot equals ax with x of 0 equals some initial condition x sub 0 can be expressed as x equals e to the ta times x sub 0. And just so that it's clear, x sub 0 is a vector of initial conditions. A is a matrix. It's in fact a square matrix. And then e to the ta is actually a matrix exponential. I realize not everybody has necessarily seen matrix exponentials before, so I'm going to give a quick introduction to what a matrix exponential is, and at least one way to calculate it, and explain the connection to eigenvalues and eigenvectors. Okay, so matrix exponential. I'll write it like this, but exp of a matrix M is defined in terms of a power series. So I plus M plus 1/2 m squared plus 1 over 3 factorial m cubed plus 1 over 4 factorial m to the 4th, and so on. And the idea here is that there's a power series for e to the x that's got this shape. And if you like, you can fill in all of the extra factorials. You can generalize analytic functions like this. So analytic means it's expressed in terms of a power series. You can generalize analytic functions to apply to matrices as well. Now, you may be wondering, how in the world would you go about calculating something like this? Well, here's a way to do this. Suppose that m can be diagonalized. This is the easiest case. In this case, you can express m, no, I drew that backwards, as v lambda v inverse. And the way this works is that v is a matrix of eigenvectors, and lambda is a diagonal matrix of eigenvalues. So for each one of these eigenvalue-eigenvector pairs, we have that m vj equals lambda j vj. What's nice about having this diagonalized formation, this diagonal expression of m, is that m squared can be written like this. And the V inverse and the V in the middle cancel out, which leaves you with V lambda squared V inverse. Then you can continue this V lambda V inverse, V lambda V inverse, V lambda V inverse to get M cubed. And now in between a bunch of times V and V inverse are multiplied together and cancel out, and you're left with V lambda cubed V inverse. In general, the nth power of the matrix M is V times lambda to the n times V inverse. But a diagonal matrix, power of a diagonal matrix is easy enough to compute. So if you have lambda 1, lambda 2, dot, 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 down the diagonal, and you raise that to the power n, that is simply the nth power down the diagonal. Now putting all of that together is that if you have this diagonal form for the matrix, you can write out the power series like this. So I plus the first order term is m, so that's v lambda v inverse. The second order term is 1 over 2 factorial v lambda squared v inverse. The third order term is 1 over 3 factorial v lambda cubed v inverse, and so on. Now you can pull a v out on one side and a v inverse out on the other side, and have I plus lambda plus 1 over 2 factorial lambda squared plus 1 over 3 factorial lambda cubed, and so on. But if you now look at what's happening and just compute all of the entries, everything in this sum now is in diagonal form. I'll get a 1 from here, plus a lambda 1 from here, plus a 1 over 2 factorial lambda 1 squared from here, and so on. That's the first diagonal entry. The second diagonal entry, I'll get a 1 from here, then I'll get a 2 from there, a lambda 2, and then I'll get 1 over 2 factorial lambda 2 squared from there. And that pattern continues all the way down the diagonal. So what we end up with is v times e to the lambda 1 on the first diagonal slot, e to the lambda 2 in the second diagonal slot, and so on. So computing matrix exponentials in the case of a diagonalizable matrix is really not too hard. So here we go, there's exp m. So going back to this differential equation, why does e to the ta solve this differential equation? Well, let's just work it out. So checking the differential equation and initial value. Okay, well, if I define x to be e to the ta, that means that x, assuming again that a can be diagonalized, I can write this as v times e to the lambda 1t, e to the lambda 2t, and so on. So checking the initial value is actually very easy. X of 0, oops, I left something out here, x sub 0. Okay, so then x of 0 is v times, well, this diagonal matrix here is going to reduce down to just ones on the diagonal. And when you simplify all of this, it simplifies down to just the identity matrix, and you'll be left with that x of 0 equals the initial condition. Another way to see this is that if x is defined to be e to the ta, e to the ti times x0, that's I plus ta plus 1/2 ta squared plus 1 over 3 factorial ta cubed, so on, times x0. So if I plug in 0 for t, I'll just get zeros all the way through. So that checks out the initial condition. Then for the derivative part, well, there's two ways to see this. One is to simply differentiate the power series one term at a time. So we get nothing for there. We get 1 times a here. And remember, we're doing the derivative with respect to t. So there we go. The derivative of t squared is 2t. And then we keep the a squared plus 1 over 3 factorial. Now we'll get 3t squared for the derivative of the t cubed times a cubed, and so on. And when you simplify this, you'll get a plus, well, you lose 1 off the factorial in each term. Now I'm going to bring a factor of a out front. I'm left with an I here, a ta here, 1 over 2 factorial t squared, now a squared here, and so on. So that means that x dot is actually a times e to the ta times x sub 0. And that part, e to the ta times x sub 0, is just x. So that's how you can check that e to the ta satisfies the initial condition. That's right here. The initial condition checks out, and also the differential equation. That holds, by the way, whether a is diagonalizable or not. The calculation of e to the ta is a little more complicated if a is not diagonalizable. I will be getting to that in a future video. Okay, so there you go. That's how to use the matrix exponential to solve a differential equation.